This video is about beta-lactam antibiotics and one of the bacterial enzymes, New Delhi Metallo-Beta-Lactamase 1, or NDM1, that renders them ineffective in the body. The overall reaction scheme for what is occurring biologically is shown here. The beta-lactam ring is opened by a nucleophilic attack on the characteristic amide bond. The nucleophilic water molecule is stabilized by NDM1, and the resulting hydrolyzed beta-lactam is unable to perform its intended function. Beta-lactam antibiotics are used to treat a wide range of bacterial infections and occur in several classes, including penicillins, cephalosporins, monobactams, and carbapenems. They are characterized by a four-membered heterocyclic ring shown here. The nitrogen in this ring binds to penicillin-binding proteins, or PBPs, in the cell membrane of bacteria. These PBPs cross-link within the cell membrane, and the beta-lactam interferes with the cross-linking process, disrupting the cell's integrity and causing the bacteria's death. These antibiotics have been used abundantly for decades, and this has promoted bacteria to evolve mechanisms of defense against beta-lactam antibiotics. To defend themselves, bacteria have evolved hydrolytic enzymes, or enzymes that cut bonds using water, that break the beta-lactam ring. The most common class of these defensive enzymes is the Metallo-Beta-Lactamase, or MBL. MBLs use a metal ion, typically zinc, in the enzyme's active site to catalyze hydrolysis of beta-lactam amide bonds, rendering the product ineffective as an antimicrobial agent. One MBL, New Delhi Metallo-Beta-Lactamase, or NDM1, is of particular interest to scientists due to its rapid spread since its discovery in 2008 in New Delhi. It can form either a dimer or a monomer, and contains 1 to 2 zinc ions in its active site. Its plasmid-encoded gene is found in pathogenic gram-negative bacteria. Evidence suggests that NDM1 obtains the zinc from solution rather than during protein processing in the Golgi. NDM1 is characterized by an alpha-beta-beta-alpha sandwich fold with the active site at the interface between domains. As you can see in both the ribbon and surface structure, the active site is in a deep cavity formed by 2 residual loops. This deep cavity allows for specificity and selectivity for the zinc ions. In addition, NDM1 is relatively flexible. This flexibility is largely due to the high number of alanine residues highlighted in green. Alanines have small side chain groups, which not only increases flexibility, but also decreases steric hindrance so that the active site can accommodate a wide range of beta-lactams that many other MBLs are unable to hydrolyze. In fact, the alanine-rich loops surrounding the active site help to position the antibiotic in such a way that the beta-lactam ring is right above the zinc ions, aiding in nucleophilic attack on the carbonyl carbon atom. This flexibility is also demonstrated by one loop in particular that adopts different conformations to allow for different substrates to be bound to the active site. When comparing this conformational shift to literature, it is clear that this one loop, highlighted in purple, is integral to the hydrolysis of bulkier substrates that other MBLs can't get close enough to the active site to hydrolyze. This flexibility allows the active site of NDM1, seen here, to accommodate several different metal ions such as cadmium, cobalt, iron, and manganese. Even though NDM1 remains catalytically active with these metal ions at the active site, there is still a preference for zinc ions biologically. I sought to explain this preference with a variety of chemical principles. One common consideration for preferential binding is ionic radius. If an ion is too big or too small, it may not be appropriate for the active site of that particular enzyme. However, the ionic radius of iron is very similar to that of zinc, not helping to explain selectivity. Another consideration is the effective charge, or Z-effective, which is mostly ordered by the Irving-Williams series. The Irving-Williams series is explained by a combination of Z-effective and ligand field stabilization energy, or LFSE. Zinc 2 has a higher Z-effective than any of the other first-row transition metals, and thus should have a higher affinity than any of them. Additionally, it has an LFSE of 0 and is thus very labile in comparison. In contrast, iron 2 has a negative LFSE and is far less labile. The final component, hard-soft acid-base theory, categorizes metals and ligands into hard or soft based on multiple characteristics. Zinc is a borderline acid and it is the softest of the 3D metals with a 2+ charge due to its position on the periodic table. Iron 2 is a hard acid. Thus, the soft base histidine and cysteine residues in the active site of NDM1 prefer zinc. Now that flexibility and the preference for zinc have been discussed, it is time to move on to the active site itself and the catalytic cycle that results from the activity of NDM1. However, there is some discrepancy in the literature regarding both the geometry of the active site and the exact mechanism of the catalytic cycle. This is largely due to the fact that no crystal structure has ever been obtained of NDM1 with solely 2 zincs. According to some literature, as seen in the figure, one of the zinc ions is coordinated by 3 histidine residues, while the other is coordinated by aspartic acid, cysteine, and histidine residues. The first zinc ion is also coordinated by a water molecule, which acts as the nucleophile while attacking the beta-lactam. However, this crystal structure was obtained with a beta-lactam complex to the zincs, which likely altered the geometry. Alternatively, some literature argues that, based on the mechanistic and spectroscopic studies performed, the geometry of the 2 zinc ions is different than found in the above crystal structure. The crystal structure of NDM1 has been obtained with 1 zinc in the zinc 1 position and a cadmium in the zinc 2 position. This causes a tetrahedral geometry for the zinc 1 ion, complexed with the same 3 histidine residues and nucleophilic water molecule. However, the cadmium is complex to 3 water molecules in addition to the histidine, cysteine, and aspartic acid residues, forming an octahedral geometry. In addition to the confusion about the geometry of NDM1, there is also dispute about the mechanism of the catalytic cycle. As shown before, the reaction scheme itself is fairly straightforward. The beta-lactam is hydrolyzed by a water molecule that has been activated and stabilized by NDM1. The 2 proposed mechanisms are fairly similar, but there is dispute about the role of the second zinc ion. In this first mechanism, the second zinc is only present to help stabilize the bridging water molecule that activates a chain of other surrounding water molecules that eventually hydrolyze the beta-lactam. In contrast with the previous mechanism, a simpler mechanism has a more active role for both zinc ions. In this mechanism, the first zinc both stabilizes the nucleophilic water molecule and helps to stabilize the carbonyl oxygen. The second zinc stabilizes the nitrogen atom as well. This crystal structure of NDM1 coordinated to a hydrolyzed ampicillin lends credence to the second mechanism discussed because of the coordination of the zinc ions to the beta-lactam. Why does this catalytic cycle take place? Firstly, the electrostatic interactions of the zinc ions, NDM1, and the beta-lactams. Secondly, a zinc behaves as a Lewis acid and is especially well suited for binding to water and lowering its pKa. The zinc ions in NDM1 activate the water molecule so that the deprotonated water can act as a nucleophile and attack the carbonyl carbon of the beta-lactam ring. The zinc ions stabilize the hydroxide, lowering its pKa, which lowers the activation energy of the nucleophilic hydrolysis reaction, thus catalyzing the reaction. As can be seen here, the first zinc ion operates in a classic 16-18 valence electron catalytic cycle. In conclusion, NDM1 is a potent beta-lactamase that can hydrolyze nearly any beta-lactam antibiotic. Its properties and behaviors can be explained through chemical principles and theories such as hard-soft acid-base theory and ligand field theory. There are many things still to learn about NDM1 to effectively design medical treatments that can inhibit both NDM1 as well as all other MBLs. Thank you.